Good morning, everybody. Um, Thank you for joining us today. Happy Thursday. My name is Anthony Connors, and I'm the regional field engineer for the Michigan and Toledo area, and I'm going to be your host for today. Real quick, I'm just going to go over a couple things you might be noticing if you're new here to these types of events. Probably have already noticed, but your camera and mic will not be on for this event. And you should be seeing on the right side of your screen handy Q&A feature. If you have any questions that come up during the presentation, please feel free to submit them there with your first and last name, and we're going to take some time at the end of the presentation here to answer your questions. But if that doesn't seem to be working for you, you can always email your questions to solutions.michigan@swagelog.com, and we'll add your questions to the list for the presenter. But with that out of the way, I would now like to welcome back Chris Kiesling. Chris is a chemical engineer with over 15 years of experience in the field before he joined us just about 3 years ago as our operations director. So without further ado, I'll now turn it over to Chris.
Yeah, thanks, Anthony. So let's get started here. If you've been with us before, you know we always start off with our agenda for the day, and we like to frame out all of our webinars by the what, when, and why on the topic at hand. So, the topic of directional flow, what are we trying to do here? We want to lay out and build systems that prevent backflow and unwanted stream mixing or contamination throughout our process. We're going to do that both during design and installation. And the why, I hit it on the what a little bit, but also here again, we want to prevent contamination of materials, and we also want to protect our components in our system, especially rotating equipment, things like pumps and other items which can't tolerate any sort of backflow. So we're going to cover today some directional flow applications, where we're going to use directional flow products. Check valve function. Check valves are going to be one of our main components that we use for that, how they function and how we select them. We're going to talk about stream selection. So that's a whole suite of valves that are offered, another way to control directional flow. And also we're going to tackle quick connects as part of that. At the end, we'll hit on how to select a quick connect and what to look for when you're using a quick connect coupling. So directional flow applications, where do we need to start thinking about directional flow? First and foremost, one of the ones is mixing lines. So this is an example of a chemical dosing system or an additive system with a static mixer. In a case like this, we want to make sure that what's flowing in our main pipe, if say those dosing pumps trip off or we have a pressure difference between the two, we might not want to backflow product back into those lines. It could affect your ratios of your mixing, or it could affect the materials if they're not tolerant of the mainline mixing or the mainline product. So again, we want to prevent contamination, prevent mixing in those cases. So we want to keep the flow direction going the direction we want it to, right? Loading systems are another common one. So an example of this is bottom loading of trucks. A lot of people top load to avoid this. But again, if you're loading this truck, excuse me, you have a pump sequencing issue, something happens, and all of a sudden you have the static pressure of the pump pushing back, or the truck pushing back into your system. You want to avoid that. So again, that's a spot where we want to think about directional flow. Finally, this is probably actually the most common, right, is on pumps. So pump discharge, frequently you really want to go from inlet to discharge. And what you'll see here is a number of pumps, 3 pumps that are on a common header here. If you want to keep your isolation valves open at all times, which is a good way to do things, because if a pump trips off, you can start another one up very quickly. In that case, you'll want to use something to make sure the flow can't go backwards through the pump. If it goes backwards through the pump, it can spin the pump backwards, which could cause damage to your equipment. So we want to avoid that if at all possible. So frequently, you're going to see some kind of device on those pumps to keep things going right. So when we go to design a system, or if we're looking at P&ID, somebody hands us a complicated P&ID like this. What are we looking for when we're determining directional flow? Well, first and foremost, we're going to look for flow arrows here and there on the side of the lines. That'll hopefully tell us which direction we're going in. But if we're looking for specific directional flow components, if we're looking to add them, some universal P&ID examples, you're going to see symbols like this. So the first two are styles of check valves. Those are pretty universal. You're going to either see that Z-type configuration with an arrow on it, or the arrow might be integrated into the crossbar of the Z to show what direction the flow is going to go in. Another one you might see on occasion is this style. This is technically for a spring check valve. Once in a while, you'll also see where the Y has a little spiral around it at the bottom to indicate where the spring sits. But again, those are going to be what you're looking for on your P&ID when you're looking at directional flow components, whether you're doing the design or trying to interpret it yourself, which direction to put those items in at. So as I mentioned, check valves are our most common product to ensure that flow keeps going the direction we want it to, and we're going to prevent backflow. There's three very common kinds. I'm sure there's more. These are the three that we deal with most often. First style is a spring style. Springs are nice because they can be installed in any geometry. You can put them vertical, horizontal, on an angle. They're going to work basically the same. They can also, certain models can be adjusted. You can adjust how much cracking pressure or how you want it to react in the system on certain styles. So if you have an adjustable spring check valve, that's kind of nice. You're not stuck with the way you buy it necessarily. Second style is a lift check valve, which we have in the center here. And the lift check valve, you've got no spring. The only moving component is this plunger, and it's affected by essentially the weight of the plunger and gravity. Now, the other nice thing is a metal-to-metal seal. Spring check valves will frequently have an elastomer of some sort in them to provide a seal, an O-ring or something. In this case, you can get a metal-to-metal seal, so you don't have to worry about as many chemical compatibility issues. One challenge with these check valves, however, is that they have to be installed in a horizontal direction because otherwise you're basically working against gravity. I'll show you how those work here in just a second. Finally, extremely common are a swing-style check valve. I've also heard these called flapper valves in plant. Technically, a flapper valve is the sealing valve in a toilet, but it works basically the same way. So you've got a disc inside that's weighted. The weight of the disc, and then also if they're installed vertically, gravity is holding that disc closed when you don't have enough pressure to push it open and allow flow. So those are our three main kinds. A little closer look at these. So first we'll start with the spring check valve. So this video shows, this is one that I had that's actually a cutaway. You can see the flow arrow on it, so you install it the right way. When we go flip it over and look at the cutaway inside, you can see the spring and the poppet assembly. And when we put air pressure behind it, it's going to push that open and allow flow to go through it. So that's our spring style check valve. If we switch over to the lift style check valve, this one's maybe a little harder to see. There's a little bit of chatter when the thing lifts up, but you can see that little plunger, it's floating up and down as I flip it back and forth. And we put air pressure in the end. The camera vibrates here a little bit, so I apologize, but again, it lifts it up, pushes that open, and you can see in the cutaway how the flow path works. Unfortunately, I did not have a swing style check valve, but again, very similar to the lift in that regard. It's just swinging on a pivot. So what are our considerations when we want to select a check valve? Well, first and foremost, we want to talk about material. So I mentioned on those lift style check valves that you don't have an elastomer, it's a metal-to-metal seal. So that's a nice feature. If you're considering other styles of check valves, and even with certain styles, they might still have a rubber gasket or some sort of gasketing material inside. So first and foremost, you want to look for those O-ring seals, and we want to make sure the materials are compatible with our system fluids. Secondly, if you've been with us on a few webinars in the past, you'll recognize the CV calculations. We've used that on a number of webinars, especially the valve and regulator side of things. I'm not going to go into it in detail here, but generally you want to calculate the CV to check to make sure your check valve has the flow capacity for your system without causing a lot of pressure drop. As you can see here, you've got the spring assembly, you've got all these other components that sit inside here. Those are going to be impedances to flow, so you have to think about whether or not you're going to have a lot of pressure drop when you integrate a check valve into your system. So best bet to do that is to do it with the CV calculation. So when we get deeper into check valves, there are some very specific check valve items that are specific only to check valves. So CV is pretty common, and elastomers, material selection, those are pretty common. And like I said, you can jump back to previous webinars to learn more about those. But check valves themselves have very specific items, being nominal cracking pressure, the cracking pressure range, reseal pressure, and back pressure. So check valves work basically on differential. So what is going to happen, the way that the check valve knows to seal up, or the way the check valve actuates, is because you have more pressure on the discharge side than you have on the inlet side. And then that spring or gravity or the weight of the element is going to help that thing seal. So your nominal cracking pressure is going to be the average pressure differential that's required to open the check valve. So again, based on differential. The cracking pressure range is your maximum minimum upstream pressure required to open the valve. So the cracking pressure itself is the inlet pressure at which you first get indication of flow. So you have both the cracking pressure, you're also going to have a cracking pressure range. We're going to define that a little bit more on the next slide. Your reseal pressure is going to be your max downstream pressure or upstream, depending on configuration. It's required to create a seal. So that's the point at which there is no indication of flow. And then back pressure is the differential that exists between the inlet and the outlet pressure. So that's how much back pressure exists on the unit itself. So in this example, if we had a back pressure of 20 psi, so that's our differential inlet to outlet. So you could be 120 versus 100 or something. If the spring rating on this check valve is 10 psi, our cracking pressure would be 30 psi. Then what's our upstream pressure? Well, it's a question mark. We don't know because, again, these numbers are all based on differential. So the same check valve with the same cracking pressure can work over a lot of different ranges. So one thing to remember too, your cracking pressure, I think a lot of people look and they'll say, well, I want a 1 PSI cracking pressure because I want it to open when I achieve 1 PSI. That's not 1 PSI static or 1 PSI in your system. That's what the differential inlet to outlet is. So you have to think about that. What sort of components do you have downstream and where your differentials are going to actually be across that unit. So we got a bunch of examples here. So if we have this check valve, it's a spring-loaded check valve. It's got a nominal cracking pressure of 1 PSI. From our catalog, the cracking pressure range is up to 4 PSI max. A reseal pressure is up to 5 PSI back pressure. So I've got all these different options here. So you can follow along and try to figure out, hey, is this going to be open or closed under these specific upstream and downstream conditions? So if you have 100 PSI upstream and 100 PSI downstream, is the valve going to be open? I prefer doing this slide when I've got a group of people in front of me so I can get you guys all the answer back to me, but feel free to answer yourself. And the answer here is going to be no. So we have no differential, right? So you're not going to expect that valve to be open under those specific conditions, okay? So if we move to 100 PSI upstream to 99 downstream, we've got a 1 PSI cracking pressure. I think naturally people would say, yeah, this is going to be open at that point. The real question, the answer here is maybe. And I think sometimes I like to, instead of maybe, say kind of. And the reason why I say kind of is because you're hitting the cracking pressure, and that's a spot where you first start to see the first little bits of material bubble through. But you have a cracking pressure range of up to 4 PSI. So when you look at 100 versus 96, now you're in that full 4 PSI cracking pressure range, and you know you're going to be wide open. So at that point, we have flow. We're going through at full flow, and you're good to go. So that's what that cracking pressure range really means, is that's the difference between getting the first indication of flow and being fully wide open and pushing all the way through. Now you're going to see that a lot more with the spring check valves because it's really a function of having the spring in there and the action of the spring. If you can imagine more pressure, it's going to compress the spring more and more. The more the spring's compressed, the more flow it's going to let through. And that's why you're going to have that range that exists. Now for 100 versus 0, hopefully everybody's going to say yes for that one, right? Tons of differential. And since we said 100 versus 0, or we said 100 versus 96 is open, move over to the right-hand side, 90 versus 100, sure, that's going to be open. And also at 95 versus 100. Now when we start to flip this equation a little bit and we have 100 versus 102. Now I did say 100 versus 1 we're saying is probably not open. I'm assuming that means it's sitting static and you first start pressure, or you first start the pressure in the system, it's closed, will it open up? Because if you're flowing at 100 PSI and you all of a sudden your pressure climbs up to 102, will it be open? The answer here is another maybe. The reason why is because if you have flow initiated to get reseal, you may need, as we set up here, that's what this up to 5 PSI back pressure for your reseal pressure. So if you're sitting static, you have 100 PSI downstream of the valve, 100 PSI upstream of the valve, and the valve's not open, it's going to stay not open, basically, is a way to think of it. If the valve's open and flowing and you have downstream pressure start to increase, when you get to 102, you might not actually seal. And the truth is it'll probably just start throttling a little bit because you will need up to 5 PSI of back pressure to fully seat that, to fully close it. So when you do have that 5 PSI, 100 versus 105, is it open? No, it's not going to be open at that point. So these are very confusing at times, and I think that's why we get a lot of questions around check valve selection. Our reseal range, you'll see that defined at times, is between the max cracking and the max reseal. So with a 100 PSI inlet, our reseal range is going to be 96 to 105. What does that mean? That's the area where we might or might not be open, or will be partially open most likely in the case that, depending on what conditions we have in our system. So moving away from check valves and talking about another option for directional control. So if we're trying to control the flow, we could use multi-valve layout, where we use different ball valves to direct to different lines or to mix different materials in with check valves. Another option is we use switching applications. So switching valves are pretty common. We have 3-way, 4-way, 5-way, and even more, but the 3, 4, and 5 are probably our most common. So first here is a 3-way valve. You have a common port where the fluid comes in, and then you can switch by turning the handle to either go one direction or the other. And this shows the porting configuration down below. So this is very nice if you're trying to control fluid flow and you're trying to select between one fluid or another, or one direction or another for the main inlet fluid. Similarly, if you need to select between more streams, you can move up to a 5-way valve. A 5-way valve operates very much in the same way, where you have one common inlet or outlet, and you have 4 different selections you can go between. So remember, is the number of ways is you subtract the common off, and that's how many different streams you switch between. So a 5-way valve has the main inlet is way number 1, and then it goes in 4 different directions, okay? Now, finally, the other option is 4-way valves. So 4-way valves, I think, are a little confusing because they operate a lot different than a 3 or a 5. 4-way valves are truly 4 stream selections. So you've got these 2, basically you're connecting 2 of the ports, and the element's going to switch between those 2 connections. So this is state A and this is state B. So where would you use something like that? Well, say something like an analyzer. So we might have 2 different lines where we want to switch between them to run through the same analyzer in our facility. So in this case, when you have the valve in position 1, you're running line A directly into the sampler, and then line B goes through a bypass. The reason why we do that is so that we keep line B flowing all the time. If you're using a simple 3-way valve for switching, line B would be deadheading, and you wouldn't get a fresh sample right away when it switches over. So when you flop it, now line A starts to bypass and line B goes in the analyzer. If you have a situation like this where you need a little help and support on here, just reach out to us and we'll be happy to help you through these kind of applications. We've done some really creative things here, including one that we created a water bypass recently for a system which will guarantee that it'll freeze-proof a cooler for a sample system. So we've done some pretty interesting applications using these 4-way switching valves. Now, one other option for stream selection is quick connects, and that's why we want to talk about quick connects at the end of here. So again, you can use a quick connect to plug into different bodies with a single stem to select between different flows. And so we've got an example on the next slide. It's going to show you that. So it's an example of a customer's setup that I snapped a picture of course, with their permission. Thought this was kind of a neat way to do things. So basically what they've got here, it's a little hard to see with this photo, but they've got a 5-way valve at the top where they can select between product A, B, or C that they're going to load. They load into these little totes, or you can vent pressure off using that same 5-way valve that's connected to a plant vent. When they connect the tote, they're able to first flush the tote out to make sure it's clean with a clean fluid that they're using. I think it was water in this case. They then had a purge. That's to make sure all the flushing material gets out of there, so there's no dilution of the final product they're loading. Then they can plug into the fill line, and that's how they've got it set up right now. They're filling the tote, so they've got the quick connect plugged into the fill line with the valve open for that. We've also got a filter here, which is a really nice feature for a quick connect because there are a lot of small flow passes, and if you don't filter, you could have problems with the operation down the line. So the advantages of quick connects for stream selection, one thing, you can error-proof things. So you can see right here, you know that you are connected to the fill line. You're not purging, you're not flushing. Another nice thing is there's no chance of cross tying. So if I just had these all plumbed together with the valves, what happens if someone opens 3 valves all at once? Well, now you've got the purge, the flush, and the fill all going at the same time. You might put your fill product and mix it with your flush in your flush tank or in your water lines, which could be bad. The other nice thing is it allows for easy expansion. So that was the discussion when I was out here that day, was they wanted to add another step where they wanted to depressurize, or essentially they were getting totes back that still had a little bit of material in the bottom from their customers, and they wanted to basically do a recovery line. So it's a really easy one. You drill a hole in the panel just to the right or wherever you want next to the flush. It's actually a much larger panel than this. This is a zoom in on it. And you can add that line to depressurize, and that could offload basically if there's anything still left in the material or in the tanks before you flush, purge, and then refill. So when you get into selection of quick connects, just a few special things here. So again, you're going to have the same questions around material compatibility. You're going to have the same things you want to answer on CVs and flows and whatnot. But some of the unique items on Quick Connect, first off, is CESO, DESO, and full flow. So you'll hear us say CESO and DESO. That's actually an acronym for single-ended shutoff and double-ended shutoff. So if you have a single-ended shutoff, that means that if you uncouple the Quick Connect, that the body will hold pressure, but the stem will not. So if you uncoupled it under pressure, you will have fluid come flowing out of the stem side, but the body will seal up. Double-ended shutoff means that both have a little, basically it's a check valve integrated in them. On the right, we see pictures of both. Now, full flow has no check valve generally in it, so that's just wide open on the inside. So if you uncouple a full flow under pressure, you're going to have fluid flow potentially out of both sides of it. So keep that in mind when you're selecting and when you're ordering. On the flow direction side, some are directional, some are not. This is an example of our QC line of Quick Connects. Those have a directional flow, so in those cases, you have to flow from body to stem. If you're using a lot of other, like for example, our QTMs or other Quick Connect products that are bidirectional flow, my tip is just stay consistent throughout your build, whether you're building a piece of equipment or a facility or whatever. If you flow body to stem every time, it means people know which way the fluid's flowing every time they couple up. So it's a helpful feature for the end user. There's also a feature you can request is keyed quick connects. So they have different colored bands on them. So an orange is keyed to only go, orange stem can only go in an orange body, black stem can only go into the black keyed body. So it basically gives a visual cue. And again, it can help prevent contamination or coupling to the wrong thing. And then finally, one thing to think about is coupling and uncoupling. You can't technically couple and uncouple them under a slight amounts of pressure, but it gets harder and harder the higher the pressure is, and it's not highly recommended to do it that way. So think about that when you're laying out your system. If you have a way to depressurize or lower the pressure to a reasonable range to be able to couple and uncouple. So finally, I want to just talk about other components where flow direction is important. These are all directional components we've talked about in other webinars. But first off, needle valves. So needle valves, because of the shape and geometry of the seat, we really want to make sure we flow from inlet to outlet on the needle valve so we get a good control over our flow. If you go backwards, the challenge is that you're not getting the same geometry over your control, and you won't get really good fine control. Secondly, if you have it plumb backwards and you're isolating or closing off that needle valve, you're going to keep continuous pressure on the valve seat itself, on the valve packing, and that could cause leakage down the line. So you want to avoid that if at all possible. That's especially if you're doing sample cylinders. You want to make sure that you put those in correctly with both flow arrows pointing away from the cylinder so that you're containing pressure adequately when transporting. On regulators, again, we want to keep flowing through. If you've done our regulator webinar, it's all about balance of pressures. If you flow backwards through it, it's basically going to shut off the regulator. That's what the regulator is meant to do. If you have excessively high pressure against that diaphragm, it's going to compress the upper spring and allow the poppet to close. So if you plumb it backwards, you won't get flow through it. And then finally on filters, you want to make sure that the filter is acting the way it's supposed to, the filter element itself, to get any particulate out of the media. Furthermore, you might want to use a check valve in a filter application, because if you ever get any backflow, it can dislodge contaminants off of that filter media and cause problems. If you ever have backflow that you knew happened through a filter, best bet is to change the element right away. So our goal was to make sure that we keep things flowing the way we wanted to. So we want to have control over our flow. We don't want to have something like this happen on our fountain. Ideally, we want fountains and flow that look like this. It's well coordinated. Everything flows the way we want it to and looks the way we want. And just FYI, there are Swagelok check valves in those fountains at the Bellagio. So our goal was to use the right components in our fluid system during our planning, install, and maintenance processes. And the goal here is, just like the fountains at the Bellagio, make sure our fluids are flowing as we intend every time. With that, we're going to kick it back over to Anthony and see if there's any questions.
Yeah, thanks, Chris. Yep, so like Chris said, we're going to take some time here to answer some of your questions. Looks like we got a couple already submitted here that we're going on throughout the webinar, so that's great to see. Just a reminder, if you do have any questions, you can feel free to submit them on the right side with your name, and we'll try to get to them here. But we'll roll right into it, Chris. Looks like first one here, we have a pre-submitted question from Lee, and he's asking, how is check valve leakage / sealing measured, and what equipment is used?
Yeah, so check valve leaking is sealage. So I'm assuming you're looking at how we figure out the leakage on the if it's uncoupled, how much leaks by on like a Sesso or a Desso stem or body. Our testing that goes onto the factory for those is based around liquid leak detector. So we do pressure cycling with a liquid leak detector to look for visual leak detection in that case. I'm not sure if you're asking that or around if they're coupled, but if you're trying to come up with a test protocol yourself to quantify, helium leak test is probably the most accurate if you're looking for really, really tight numbers on that. But as far as how we factory test everything, that's all, it's with pressure impulsation and with a visual leak detector like a Snoop.
Yep, great. So next one, we have another pre-submitted question here. This one's from Jeff. And it looks like he's got a pretty specific application here. He's saying would an SSCH12-1/3 for sour gas service be able to handle a normal flow rate? And then he's got 400, 800, and 900 CCMs with steady back pressure. And then he also asks, would it be able to handle a high flow rate of 5 to 6 liters per minute?
Yeah, so I want to thank Jeff for pre-submitting that question because there's no way I would have figured that out on the fly. So I had a couple days to look through that one the other day. So first off, if it's a sour gas application, you want to make sure that you are purchasing or ordering NACE compliant components. If you go later in the catalog towards the back of that catalog on the Quick Connect side, for sour gas specifically on QCs, you do not want to use stainless. You want to use Manal. So instead of SS, it should be an M at the beginning, and then at the end you want to add -SG after the part number but before the cracking pressure. So if it was like, I think you had SS-CH12 1/3, I believe, or 1.
Yeah. Yep.
Yeah, so instead what you want to do for sour gas applications is do an M-CH12 SG 1/3. So get that out of the way first. Secondly, I took a look at the flow charts and took a look at the CV calculations, and it looks like you're going to be fine with that flow rate. You'll have about a 2 to 3 PSI pressure drop. When I looked at that, the CH12 is a 3/4 inch in connection. It's actually uses the CH16 style body, which has a CV of 4.7. When I calculated even at your high flow, you were less than 1 CV required. Now I had to make some guesses on your fluid that you're using and your temperatures, so you might want to just double check that in the CV calculator yourself. The CVs for those, based on which body you're using, is at the beginning of that catalog. If you need any more help, you can let your guys know. I believe it'll be AJ or Rick, and I'd be happy to help you more if you need something on that.
Yeah, thanks again for the question, Jeff. Moving on here, we have another pre-submitted question from Janet, and she's asking, is there a directional flow for Quick Connects, and what is the best practice for installation?
Yeah, great. So I think I covered it slightly in the presentation, but generally some of them are, some of them aren't. It depends on the series or the style you're getting. The ones that are directional, I believe all of our directional runs flow from body to stem. And generally, I say, like, rule of thumb, if you always keep body to stem flow, then everyone will always know in whatever you're building, whether it's a piece of equipment or maintaining a facility, if it's always body to stem, you'll always know the flow direction. So even if it's a bidirectional flow, using body to stem as the flow direction on Quick Connects is always a good way to approach things.
Great. Yep. We got a couple more here, looks like. I'm going to jump around here. So this next one, this person is asking, are there check valves that can be inserted into a manifold but be below another component, like a filter?
Oh, that's a great question. Check valve inserted into a manifold below another component. I would love to talk to you more about that one, so I can really make sure I can think of what exactly you've got going on there. The one challenge you're going to have is if that filter downstream causes a lot of back pressure, you want to make sure that you have enough pressure in the manifold to overcome basically whatever your downstream is plus your back pressure. I didn't really cover it in the presentation much, but you have to think about things like if your discharge tubing is really, really long and going straight vertical, you have to worry about the head pressure and what that's going to do for differential. So say, for example, if you've got if you're pressure limited on the discharge of a check valve to 100 PSI, plus you're going up 50 feet in the air and your pump only puts out, say, 105 PSI, you might actually, all those things, those discharge or those downstream components added all up that are causing pressure drop, you might not be pushing the check valve open with the pump capacity that you have. That's probably the most complicated way possible for me to answer your question, but the answer is you're probably okay based on selection. Just consider what you're expecting your pressure drop to be, or your differential pressure is downstream because of any components you have coming on. Now, the one other thing I'll challenge you on is if it's a manifold and it's got a bunch of things, a bunch of different things coming off of this one manifold. Even if the check valve's open, it can affect the manifold pressure at that point, right? So you could have the check valve open, but your manifold's going to be basically whatever back pressure comes from all your downstream components from all the different bits and pieces. So I'm sure you're already dealing with that anyway, so it's probably not that big of a deal.
All right, and then last question here, Chris, super quick. Sam's asking, can I use a check valve as a relief valve?
Yeah, so it's not highly recommended. It's people do it. We do have, we make caps that are technically, obviously that's what they're for. We do not recommend, we recommend using relief valves. For relief valves, it's going to give you more of the features that you're looking for. Relief valves are really all about maintaining that system pressure where you want it. Check valves are really more about maintaining flow. So it is possible if you can't find exactly the relief valve application you want. But again, your best bet is always to try to stay in the world of relief valves. That's going to give you the best overall performance, especially on the Reseal side.
Yeah, definitely. Yep, you just have to remember what the function of the two valves are. But all right, yeah, that's all the time we're going to take here for questions. We're kind of hitting the 10:30 mark here, but thank you everybody for who submitted a question. If we didn't get to your question, we'll be following up by email. And if you have one that comes up after the webinar, you can always reach out to us or your account managers. But just a couple of things to wrap up here on now. If you were present here during the webinar, you'll be receiving a couple of follow-up emails with some reference documents. We have a nice blog and video here that'll kind of help you with your selections. And we also want to make sure that you're joining us here for the next webinar where we'll be going over valve selection. That'll be next month here for May. And again, thank you all for joining us here today. If you have any questions, feel free to submit them to solutions.michigan@swagelock.com. And thank you again for joining us. And please visit our website at michigan.swagelock.com. Thank you all and have a great rest of the day.
Thanks, everybody.